So we have a match the column type question. Alpha and beta be the distinct roots of this equation. So we have that alpha plus beta equals to -1. Okay, Ri is the sum of the ith row, Cj is the sum of the jth column. So let's start with P. Given the number of, we have to find the number of matrices such that the sum of each row and sum of each column is 0. And the element should be from T. So if the sum of a row or column is 0, then the elements should be 1, alpha and beta. All the three should be there. So 1 is 1, another element is alpha, the third element is beta. Because in any other configuration, the sum won't come out to be 0. So let's start with the first row. We have 6 possible permutations of 1, alpha and beta to decide for the first row. Say we go with 1, alpha and beta. So there are 6 possible permutations. Now for the second row, so each column must also contain 1, alpha and beta, all the 3 elements. So below 1 we cannot have 1. So we can have either alpha or beta. So there are 2 possibilities. And if we decide we want alpha here, so beta cannot be here, so beta will be here, and we'll have 1 here. So that pretty much locks the position of these two, and it also determines the third column because 1 and alpha are here, so beta should be here, and 1 should be here, and beta and 1 are here, so alpha should be here. So basically out of the 6 possibilities we can choose any one. For each of them we'll have 2 possible choices for the second row, and the third row would be determined completely by what we choose for first and second row. So we have 12 different configurations possible. So P is matched to 2. Let's check Q. Number of symmetric matrices with all entries in T such that the sum of each column is 0. So each column must have exactly 1 alpha, beta, and exactly 1, 1. So again we have 6 possibilities for the first row. Let's say we go with 1 alpha and beta. This determines the first column as well because it's a symmetric matrix. Now let's look at this position. This cannot have a beta here because this column already has a beta. This cannot have an alpha here because then as this is a symmetric matrix, we'll have an alpha here, but this column already has an alpha. So that means the position, the element here is determined by what choice our first row, by the choice of a first row. So we get a 1 here, so that makes 1 here, and as each column must have exactly 1 alpha, beta, and 1, so we'll have beta here and alpha here. So by the choice of our first row, the entire matrix is determined. So the number of possible choices we have are 6. All the 6 permutations of 1 alpha and beta. So Q is mapped to 4. First let's check S. Be a matrix with all entries in T such that Ri, that sum of each row is 0. This is really easy. Sum of the R1, sum of all the 3 elements is 0. R2, sum of each element is 0. R3, sum of each element is 0. That means we must have 1 alpha and beta, 1 of each in each row. Say beta alpha 1 or gamma 1 alpha 1 beta, anything. But as sum of each row is 0, so we'll just make the transformation C1 goes to C1 plus C2 plus C3. This should not change the value of the determinant as we know, but that will make the first column as R1, R2, R3 and whatever elements we had here. And since each of these are 0, the entire first column becomes 0. So the determinant value should be 0. So S is mapped to 5. Now let's see the option R. Be a skew symmetric matrix. Let's say M is 0, A, B, C, 0, 0, minus A, minus B, minus C. And we are given that A, B and C are from T. So there must be one of 1 alpha beta. This into X, Y, Z is equals to A12 is minus A0, minus A23 is A32, which is C. So we get minus AY minus BZ equals to minus A, and AX minus CZ equals to 0, and BX plus CY equals to C. Multiplying the first equation by minus 1, all the minus signs will go away. So we get this. So we have BZ equals to A into 1 minus Y, AX equals to CZ, BX equals to C into 1 minus Y. Let's for a second replace 1 minus Y by Y prime, which gives us, so basically this system of equation cannot be solved. For basically we can reduce two of these and to the third one. So what we'll do is we multiply this by A and this will multiply by B. So equating these two, we get BCZ equals to ACY prime, and since C is from T, so it's non-zero, so C, we can cancel out C. We get the third equation. That means there are infinite number of solutions for this system of equation. So R is mapped to 3.